Hi everyone, my name is Vishrant Tripathi and today I'm going to present our work titled Online Learning for Indexable Restless Multi-Arm Bandits. This is joint work with my advisor, Professor Eitan Modiano. Let's get started. So first I will go over a brief outline of the presentation today. The first thing that I will discuss is Restless Multi-Arm Bandits. So I will go over a brief overview of what these are and how to solve them. Typically, the way you solve restless multi-arm bandit problems is by establishing a special property called indexability, and then using this property to construct a low complexity near optimal solution called the Whittle index. That is what we will discuss second. Third, I will formulate an online formulation of the restless multi-arm bandit problem in which you have episodes, and in each episode you need to solve a new version of a restless multi-arm bandit problem. In this online learning formulation, we will propose an algorithm called Follow-the-Perturbed-Whittle-Leader based on Follow-the-Perturbed-Leader style of algorithms from online learning literature. And we will see how this algorithm is suitably adapted to this restless multi-arm bandit framework and performing online learning in this episodic setting. At the end, I will briefly discuss the application of this online learning framework to wireless scheduling problem for mobility tracking. So let's start with something that's familiar to most people who are attending the student conference. It's the classical Bernoulli multi-arm bandit problem. In this setting, you have n arms, each of which just gives a Bernoulli reward with some probability p. And what you want to do is choose the arm with the highest probability of success or reward. And the setting of interest here is when you don't know the probabilities of reward for each arm beforehand and you want to learn the best arm. The motivation for this area comes from learning literature. What we will look at is a slightly different form of multi-arm bandits. The simplest form of these multi-arm bandits is Markov multi-arm bandits. And here, instead of having a Bernoulli arm, each arm is instead a Markov chain. And the arm evolves on a state space S based on a probability law P and returns rewards which map the state to a reward. And the most interesting part of the Markov multi-arm bandits is that when a particular arm is activated or pulled, it evolves according to this Markov law. And when it is not pulled, it remains at rest. So the state does not change. The setting of interest in Markov multi-arm bandits is to find the optimal policy or the optimal way to schedule these arms so as to maximize long-term average reward. And even just doing this, when you know all the information about the arms, which means the state spaces, their probability transition laws, and the reward function mapping, is a fairly hard problem. It was shown in 1970s by Gittins and his collaborators that the optimal policy can be computed efficiently, and it uses an index structure. So if you want to naively solve the dynamic programming problem to compute the optimal policy, then that would be a very hard problem to solve computationally. But Gittins showed that this problem could actually be solved efficiently for any kind of Markov multi-arm bandit problems. Restless multi-arm bandit problems are an even bigger generalization of Markov multi-arm bandit problems. So the key difference between restless and Markov multi-arm bandits is that even when a particular arm is not activated, it still evolves according to some Markov transition law. So each arm is a Markov chain with two possible transition laws. If it is activated, it evolves according to one law. If it is not activated and at rest, then it evolves according to a different law. And this setting of interest, again, is trying to find the best scheduling policy and the right order in which to schedule these arms so as to maximize long-term average reward. Whittle extended the work of Gittins in 1970s to restless multi-arm bandits in 1980s. And what he showed was that a near optimal policy, not an exactly optimal, but a near optimal policy can be computed efficiently for a special class of restless multi-arm bandit problems, which satisfy a property called indexability. And this indexability property is something that we will discuss briefly in the next slide. Now, one of the things to realize here is that restless multi-arm bandit problems are much harder to solve than just Markov multi-arm bandit problems. In fact, it was shown by Tsitsiklis and Papadimitru also in the 1980s, in the 1990s, in fact, that solving general restless multi-arm bandit problems is EXP complete. So the indexability property is a property that is roughly akin to monotonicity. And what it does is it allows each arm's optimization to be decoupled using a Lagrange multiplier. And this is the key idea of the Whittle approach. So what you can do is, instead of solving this coupled problem with n arms for a very long time, you can decouple the problem for each arm, solve these decoupled problems separately, and then combine the solution together to get a near optimal policy. And the way you solve these decoupled problems is by computing something called index functions, which basically denote how valuable it is to activate a particular arm at any given state for that particular arm. And once you calculate these index functions, the Whittle index policy is simply to take the Whittle index of all the current states of each arm and choose the arm that appears to be most valuable. Okay, so now that we have specified what the restless multi-arm bandit problem is, what indexability is, and how to compute the Whittle index, we will formulate an online learning problem based on the restless multi-arm bandits. So this is an episodic version in which the problem designer receives a new restless multi-arm bandit problem to solve at the beginning of each episode. He decides, so the first thing that the problem designer decides is he chooses an arm activation policy, after which a restless multi-arm bandit problem is revealed to him, and then the episode runs. Once the episode ends, the designer chooses a new arm activation policy, and then another restless multi-arm bandit problem is revealed to him, and then the episode runs, and this process continues. Each episode is fairly long, so we assume that the length of the episodes is m time slots. The two key assumptions that we make are that the arms, state spaces, and transition laws remain fixed across epochs. So this is the same family of restless multi-arm bandits that you keep solving in every episode, and you know the structure beforehand. But the reward functions that map the states to rewards, which are real numbers, can change arbitrarily across epochs in an unknown and possibly adversarial manner. The only condition that we put on these reward functions is that they still maintain indexability, so that we have some way to compute reasonably efficient solutions. Otherwise, there is no way to actually compute efficient solutions. The question that we want to ask in this online learning framework is that, can we design a scheme that learns the best scheduling policy across these epochs in an online manner? So can we design an arm activation policy that adapts as the reward functions change? And the answer is yes. So one way to naively solve this online learning problem is to consider something called Follow-the-Perturbed-Leader. This is a classical online learning algorithm proposed starting in 1950s. And the way to apply Follow-the-Perturbed-Leader to this kind of a problem would be to view arm activation policies as experts. And at each episode, what Follow-the-Perturbed-Leader would do is the following. It would maintain the sum of the rewards observed in the past for all episodes. It will perturb these rewards IID for each scheduling policy, and then optimize across these scheduling policies for this perturbed history. The issue with this method is that the number of policies scales exponentially in the length of the epoch. So it scales as n to the power m, but n is the number of arms and m is the length of the epoch. And you can see that steps 2 and 3 take computational complexity linear in the number of experts or the number of scheduling policies. So traditional online learning methods are infeasible here. Even if you try something like EXP3, it still involves sampling distributions over the space of all possible experts, which is, again, takes linear computational complexity. So all traditional online learning methods are infeasible here. What we propose instead is a different method called Follow-the-Perturbed-Whittle-Index, which involves two key ideas. The first one is that the Whittle index acts like a low complexity optimization oracle for the restless multi-arm bandit problem. So what we should do is we should incorporate it in Follow-the-Perturbed-Leader. So instead of doing step 3, where we optimize using the entire perturbed history, we use the restless multi-arm bandit Whittle index framework to do this optimization in a computationally efficient way. The second idea is that instead of perturbing the costs of policies, we perturb the reward functions themselves. Note that the reward functions themselves are simply scaled by the number of arms and the size of the state space. So it scales linearly in the state space and the number of arms, and not with the length of the epoch. And the issue with Follow-the-Perturbed-Whittle index now is that it introduces new technical challenges. The first one being that the perturbations are now such that they are to the reward functions, but we require that the reward functions be indexable. So the way we create these perturbations should maintain indexability structure. The second one is that perturbations are no longer IID per expert or scheduling policy. This is an essential assumption for the proof of regret analysis for Follow-the-Perturbed-Leader to go through. However, this does not remain true any longer because we need to maintain indexability. And the third one is that the Whittle index is only an approximate optimizer, but not an exact optimizer. So we need to figure out a way to handle all these challenges and do new regret analysis. And our major contribution of the paper is proposing Follow-the-Perturbed-Whittle index and then resolving these challenges and showing that this can indeed be done and we can get a reasonable regret bound for this kind of an online learning framework. So that sort of summarizes our key theoretical contributions. A brief description of what we try to apply to in a more realistic setting is a problem in wireless scheduling. So what we look at is monitoring a large number of sources with possibly unknown and time-varying dynamics over a wireless network. So the issue here is that only one source can talk to the base station at a time because this is a wireless network. And we want to design scheduling policies to figure out which source should get priority to talk to the base station. The issue is that sometimes a source is varying very quickly, so it should have higher priority. Sometimes it's varying slowly, so it should have a lower priority. And so the static problem in which you know the rates at which each of these sources evolve and they remain fixed, that can be formulated as an indexable restless multi-arm bandit problem. This is a result from some of our prior works. And what we show in this paper is that for an online problem, we can apply our framework and do this indexable restless multi-arm bandit online learning to get better policies. So what we simulate is a specific form of time-varying mobility called Levy mobility, which is considered to be a very realistic model for simulating human and car mobility, for example. And what we show is that for this time-varying Levy mobility pattern, Follow-the-Perturbed-Whittle-Leader kind of algorithms outperform standard algorithms such as round robin or maximum age of information algorithms, which just optimize for information freshness rather than actually optimizing for the monitoring error. And that's it. Thank you.